Yeah, so good morning, everyone, and thanks to the organizers and to IPAM for having me here to talk about some of our work. This has been a very enlightening workshop this week. So even though I'm giving a talk here, I still feel like a newcomer into this area of equity. In fact, the work that we're talking about today, none of it is published yet, so feedback is very welcome. Right, so this is joint work with three of my PhD students, Bingting Liu, Farnoosh Namdapur, and Shiron Ren, two of which are on the job market. So if you know of any postdoc or faculty positions, please feel free to share. And it's also collaboration with Pratik Bansal from NUS and Chenghe Guan from NYU Shanghai. Okay, so there's been a lot of different talks this week, from philosophers, urban planners, mathematicians, social scientists, behavioral scientists. My perspective here is more as a transportation engineer, right? So I try to look at this problem of how do we incorporate equity into transportation analysis from that point of view, right? And try to distill that into specific problems that we are interested in. And kind of the two areas, and note I also try to add in the Lorenz curve to add to the quota, right? So two of the questions are who makes up our population? Really to be able to understand how to address that problem, one of the key questions is trying to understand who makes up our population. And the other question is how the transportation system, the way that it's designed, impacts each and every one of us, right? As far as we can distinguish that population. And this has, so from my point of view, I was looking at this as kind of what are the challenges that transportation engineers would face in trying to tackle with these challenges, these specific problems. And there are two data implications that we were trying to grapple with. Right? One is when we look at the data, are they capturing everyone representatively? And the second question is, can we tractably, and I mention this because it's great that Irene gave her presentation just before this, and thematically, the methods that I'll talk about, which includes zone design and choice modeling as well, they actually, there are challenges to try to use existing methods to integrate the response of travelers, of a diverse set of travelers, to impacts of different transportation designs. Right, so that's the commonality that drives this talk, right? In terms of how do we organize the data, or even how do we reorganize the way we think about restrictions on the assumptions we make about the data in terms of specifications for models for transport modeling. Okay. So the outline is broken down into those two broad questions, where one is, can we reorganize data to better represent underserved groups? And the second one is, can we integrate choice models with service optimization in a way that doesn't really require restricting their specifications too much? And of course, there are choice modeling experts here that I would defer to later and ask for feedback after this. All right, so to begin with, in a lot of the topics that even some of the presentations that were given here in this workshop, when we talk about ways that we optimize transportation models, oftentimes there's an underlying assumption that the demand data is all true, right? That it's the ground truth, right? It's infallible, despite that there's a lot of evidence to the contrary, right? So this is a study from just a few years back from Yinhai Wang's group looking at equity biases in transportation data. Right? One of the key ones of which is coverage bias, and that's one of the ones that I do want to focus on. Right? The fact that there's oftentimes undersampling or oversampling systematically that can misrepresent populations. And there's a consequence to this, right? Because it's not just looking at the data itself, but when we take a look at the process, the pipeline of how we model transportation systems after that, there's a potential, right? This has been studied for many years back already, right? So some of the work from Carol Cockerman's group, for example, in the early 2000s, have shown that there's propagation of uncertainty in travel demand models that can be amplified as you consider more models that you kind of process together, right? And so it really adds to that need to really track down the source of the problem, the data itself, and try to better understand that. And so there's a lot of different types of models out there, and we wanted to find like a kind of a representative model use case to tackle this data issue. So we started with population synthesis. All right, so what is population synthesis? It's basically a way of trying to create synthetic data in a way it's producing very high resolution synthetic data. So for example, in this process that we see here, we would produce the actual locations and numbers of people of different households with various attributes, right? Gender, age, income level, et cetera, in a way such that the distribution of those synthesized people fit into distributions that align well with sample data out there, right? Like public use microsample. And at a zonal level, right, that's predetermined from the population synthesis, at a particular zonal level, they match up to totals that they find, right? What they regard as the ground truth, right? Right, so I point out American Community Survey as one example of that, where you might use that data to have census tract level or maybe slightly higher aggregation levels of zonal totals. And they use methods like iterative proportional fitting, although more recently there's other techniques incorporating deep learning and such to try to better learn these with not as much data requirements as before. So some of that, this figure itself is produced from Wolf Moko's group. Okay, so when we talk about population synthesis, I mentioned that the assumption is that you're trying to match up totals at the zonal levels, assuming that they're ground truth. But in reality, and this is pointed out in this other study in 2013 from Bilal Farouk and his former supervisor, Michel Bellard, they looked at population synthesis and showed that, or at least pointed out that one of the ongoing problems with these kinds of techniques is that they assume that ground truth is the reality, even though there's a lot of other various reasons that they might be biased or systematically tampered because of for like data imputation purposes, or even just the aggregation level itself, which I highlight here, can lead to differing results, right? So then, if that's the case, how bad can that be, right? We took a look at the American Community Survey, right? So we pulled up some sample census tracts. This is one in Manhattan, in New York City, right? So New York City, it's pretty diverse, and we would expect there's a good high-level density for population representation across different population segments, right? But if you just looking at age group for now, if we break that up into different categories, we can see that for some of the underrepresented groups, the margins of error can be pretty high, right? And this makes sense, right? We have government agencies. They have limited resources to collect this kind of data, and so they try to sample as best they can to capture total representation. But in doing so, there's no guarantee that underrepresented samples are well represented. Right? And furthermore, if we look at other dimensions of other types of underrepresented groups in terms of disabilities, of ethnicity, and so forth, there's also these staggeringly high margins of error. And it's something that causes concern, right? So if we were to do a population synthesis using zone control at the census tract level, assuming that the populations for these different groups are ground truth, are absolutely correct, that can be pretty problematic, right? And so it brings us to this question of how can we then design or reorganize the data in a way that might be a little bit more suitable for the subsequent modeling process, right? In which case, in this case, we're looking at population synthesis. Yes, question?
This might be a really naive question, so sorry in advance, but like PUM's data comes with like alternative sampling weights, right?
Yes.
So in this field, is it just like common to simulate over all the alternative sampling weights and like see what the...
I mean, so in that case, you take into account those sampling weights too, right? So in trying to establish the distribution, you are taking that into account. But but when you're looking at the zonal totals, they typically they'll just take those. It'll be weighted totals, right? But it's like the totals are not necessarily, those are averages, right? So there's possibility for error, right?
Right. I guess I was thinking like I don't know how these get used in transportation models. I was thinking like really what I have is a bunch of different instantiations of my zone based on all the different PUMs sampling weights. And so I can like look at the distribution of whatever your model says over the distribution of what all the realized zones could actually be.
So absolutely. So you can maintain having those metrics so you can have some measure of reliability of the models. But the problem is when you start having very complex transportation models, oftentimes it's hard to carry that over, right? So in fact, later I'll demonstrate with just a simple Monte Carlo simulation of this data and then inputting that into the population synthesis function to show you.
Thank you.
Tiara.
So just adding to the comment, so at least with demand models, it's usually not advised to include the weighting in the modeling. And then the second thing is that it's still a sample weight that's based on some ground truth that's already flawed. And so you're not introducing new information on who's missing. You're just upweighting the observations that you already have in data.
That's very helpful.
Yeah, thank you. All right. So yeah, as we can see, with the ACS, for example, the sample size is pretty small, right? So this is a challenge, and we try to overcome that. So the question is, so that we were trying to address was actually looking at zone design. So we wanted to say, well, census tract is too disaggregate to have reliable results. Is there a higher level of aggregation, and how should we design that aggregation to make it make sense? Right? You want to have as disaggregate as possible, but at the same time, too disaggregate can lead to these errors being overblown. Right, but having aggregation itself is a non-trivial problem, right? So these are looking at this data set aggregated in two different levels, and you can see the averages are the same, but the standard deviations would then change, right? And even for the same number of aggregations, right, where we have 4 zones and 4 zones for this initial data, the averages can end up being different. And so there's this problem, which is called the Modifiable Areal Unit Problem. I see a couple of people nodding their heads, right? That encompasses this kind of challenge, right? So we want to be able to optimize a set of zones that can at least take these challenges into account, right? So this is just to illustrate, right? So this is a set of zones in Lower Manhattan, where the so these are margins of errors for the populations below poverty level, and if you were to aggregate these 3 zones together, at that level, the margin of error would be that amount, right? So it's a way to potentially have, it's basically telling ourselves what are we comfortable with, right? What level of aggregation are we actually comfortable with? But at that aggregation level, there's different ways to design that. All right, so we also look at a districting problem here, right? Where the basic, so we start with basic spatial units, in this case, census tracts, right? And we're trying to determine aggregations of these. So we're determining zones or partitions where one zone is comprised of one or more BSUs, right? So in trying to formulate this as an optimization model, we have binary decisions for whether a zone is selected. So this is looking at it in terms of having an enumerated set of zones, which is a different perspective from what Irene was talking about earlier, where she's referring to growing out specific BSUs together, right? So here we're looking at this as a kind of a set partitioning formulation. So so we're identifying all the different zones, which and I'll explain why we do that, right? So we have an attribute that we might be concerned with, such as looking at the age or income level. So there could be multiple attributes that we're concerned with to try to make sure the measure of the margin of error is falling within a threshold. So there's some kind of capacity constraint related to the measure of the margin of error. Okay, and so this is the notation I'm using for margin of error. Okay, for the y attribute, and we require that every BSU is only covered by one zone. Right. So the challenge with this formulation with, let's say, the American Community Survey data that we were using is that the ACS data that they provide margins of error, but for privacy purposes, they don't share the sample size details with us. So we don't have a very precise way to aggregate up margins of error for different areas, right, when you try to add them up. There are tools like variance replicate tables that ACS provides as a way to approximate that aggregation. And that's something that we can use. But because of using this, we cannot pre-process for, say, like a lookup table for MOE at different aggregation levels such that we can incorporate it as a linear constraint. Right? So it's not easy to do that. And that's the reason why we thought to look at this problem as first, just to present it as essentially enumerating all the different zone designs and then trying to select the subset of zones that covers everything together. Thinking of it like in vehicle routing problem, for example, the set partitioning formulation, you identify all the tours, and then you're making sure the set of tours would cover all the destinations that you want to visit, right? Similar to that. And the objective here is that we're trying to minimize the intrazonal heterogeneity, which is captured by this difference in those attribute measures, and at the same time trying to maximize the number of zones, so to have it as small as possible, ensuring that only one BSU, each BSU is covered by one zone, and the margin of errors fall within that threshold, right? But because of this enumeration, it's not practical to actually try to solve this in an exact manner using enumeration, right? So perhaps column generation approaches might be able to tackle this challenge. But at the time when we formulated this, we went with the easier way, just implementing a heuristic. Okay, so for our heuristic, the way that we designed this was to have a two-stage approach, where the first stage was just generating a feasible set of zones, and that involved initially randomly sampling a set of seed locations, initial BSUs that we would grow out the zones from, right? And then after we have those set of zones where we require that they fall within this constraint, because we can post-process those designs, we can then run like a meta-heuristic, like taboo search, to swap out different BSUs between zones to try to improve the solution. Right, so that's the approach that we took for this problem. And to illustrate that, this is a 3x3 grid of different BSUs where you can see initially we grow out different zones. So we end up with 4 different zones, color-coded. Right? And you can see that we then consider switching, right, with taboo search. So looking at switching the BSU number 8 from one zone to another, and then another iteration where BSU 6 is swapped from one to another. Right? So this is this process that we would then keep repeating to try to improve the solution. So how well does this particular zone design from this heuristic work? We first try to evaluate this at a small level, looking at Lower Manhattan, and comparing it to existing aggregations of zones, zone designs. So one existing one is the neighborhood tabulation area in New York City. These are pretty large. So in Lower Manhattan, so this is the NTA design for Lower Manhattan, 6 areas in this region. And we can calculate the MOE for a population over 67 and the heterogeneity as well. So about based on our heterogeneity metric. From our heuristic, we can see that there's a reduction in the margin of error, and also more significantly, the heterogeneity drops significantly, right? So note that one constraint that we didn't really consider was the compactness. So here we designed the zones for contiguity, but we didn't capture the compactness, which is something we might consider incorporating later. Right. Another zone design, maybe a lot of people working on ride-hailing might be familiar with, are the taxi zones in New York. Right. So these are smaller areas. In Lower Manhattan, there's about 19 taxi zones in that area, and the MOE to try to capture the same number of 19 zones that we ended up with the heuristic was a little bit higher, but again, the heterogeneity drops significantly. Okay. So this seems a little bit promising, right? So we tried to implement this for 3 dimensions, looking at generating these proprietary zones. I'll call them proprietary zones. I think in our data set that's online, we call them equity zones, but I know I don't want to stir too many problems with that naming. Okay, so we looked at 3 dimensions, looking at seniors, low incomes, population, and people that take over an hour to commute to their destination. And this is just looking at the number of iterations, how the improvements converges, or at least reaches that low point. So we take the initial census tracts, 2,000 of them, throughout the whole city of New York, and aggregate them up to about 500-something zones. This is the 500-something zone design that we ended up with. And if we look at the average errors, right, the margins of errors for each of these 3 groups across all the different zones, you can see significant improvements, right? Well, these are relative to those numbers, right? So for age 67 and above, it's about a 7 percentage point reduction, right, in that margin of error, which seems promising. So then we wanted to then process this actual data set into a synthetic population process and actually compare, like if we did synthetic population using some census tracts versus if we use it using our proprietary zones, but keeping into account the fact that the original data has margins of error. So basically we simulate realizations of that ground truth and process each of them to compare, right? So that's the experimental design for this piece here, right? Where we wanted to see how that error savings actually translate when we incorporate it into an analysis process, right? So we generated 30 different ground truths of this population. We try to keep things simple, so we just focus on age, population age, right? And keeping just like a minimal set of metrics with this. Aggregated this up to the census populations up to the proprietary zones, ran an existing tool for population synthesis called PopGen, okay? It's a pretty widely used tool in population synthesis. And as the benchmark, we compared it against running PopGen with the same 30 populations at the census tract level, and from which the outputs were then aggregated up to our zone level to have consistent comparisons, right? So if we look at the resulting standard deviations, it doesn't seem like there's a lot of difference, but keeping in mind that the percentage point reduction was about 7% in any case, right? So it does seem like there is a translation of this error difference that goes into the transportation modeling process, right? So something to be aware of when we're conducting our analysis, particularly if we're interested in equity analysis and having proper representation of underrepresented groups, right? This data is all available on Zenodo. This was a C2 Smart funded project, publicly accessible from the federal agency. We also have since used this technique at the statewide level. So we have an ongoing project right now with New York State, it's with another UTC project, but using data from New York State, where we currently synthesize, or we're about to get into the population synthesis, but we're designing zones at that level too. So this work is credit to Hai or Marshall Yang. All right. So just 3 points that I want to bring up before I continue. All right. So first is there's existing data collected for populations that may undersample underrepresented groups. We try to mitigate this bias for improving data reliability for transport modeling. And the method that we did involves a heuristic to optimize a districting problem that involves the challenge of having that MOE aggregation approximation. Okay. Any questions before I keep going, Amanda?
First, it looked like you were oversampling. You were downward correcting for all of these three groups. Am I wrong? Is that true? Looking at the table,
yeah.
You were downward correcting each of them, so it's the opposite bias to what you cite here.
Okay.
What here was finding, right?
Yeah, maybe the terminology might not be appropriate. Yeah, yeah. That's
yeah, I mean, that might be less problematic. Oversampling and like, weighing people smaller, at least you have the diversity and the sample size you need to do good modeling. It's less severe problem than undersampling the groups that you're interested in, right? So like that might be worth discussing. And then just, I'm always a little like worried when I get the point of optimizing and rezoning and mapping, and like I think that's really interesting. But it's also a little risky because if you then want to merge it with other data that has the more conventional zoning, it becomes difficult, right? Because maybe it would be nice to have a criteria to make it like maximally compatible with EPA and ACS and all these different other data that maybe you have new ideas later. Yeah. You're no longer able to incorporate those controls because you have done your optimized rezoning rule, and then it's no longer seamlessly compatible with many other data sources. Yeah, no, that's a great point. I mean, so the trade-off with aggregating up zones is you lose the resolution at the lower level, and there could be that consistency with other not just resolution, because you're not using a conventionally understood shape. Right. It might be This may be something to discuss in like the trade-off. Yeah, and that's something like I think so. When we talk with like our MPO in New York, that's something they might be interested in about.
Sorry, I missed where you got your ground truth from.
So we were looking at the ACS data, American Community Survey.
So that's your.
That's our. Truth. Well, yeah, and then so when we were comparing the numbers, so that data includes margins of error associated with them. So we were comparing how. If we simulated the margin of errors into the ground truth, so we would have different representations of ground truth. Well, I mean, just the ACS data. So, it's just,
I'm just wondering, thinking of Amanda's comment. So you create zones, larger zones, which you would then also use in transport modeling. I assume. That in itself is also probably the larger the zones. The more you start averaging travel behavior, the less sensitive you can be to public transport supply, where densest and within zones to public transport are very important. More trips disappear because you don't cross zones anymore. So you have all kinds of impacts which...
Those are excellent points, So there's also those issues that you have to take into account when trying to aggregate up the zones to, making sure intrazonal or interzonal trips and such have to be considered too.
So I think, so my question is, thank you for your presentation. I think this is really
not over yet, huh?
I'm not done. Halfway.
I'm sorry.
I might have to.
Jumping the gun. But anyway, my quick question is clarification. So I thought that you said that you simulated the margin of error into the whatever the estimate is.
Yes. For that.
Does that mean that you're trying to do some sensitivity analysis and understand, like, okay, if it's
we wanted to see.
Okay.
Yeah, we want to see how they propagate. So yeah, it's kind of it's like a sensitivity analysis, right? Where you're looking at the data. So because prior to that experiment with the population synthesis, we're just looking at we see the change in data, but data quality with the margins of error, but we don't actually see how that translates into like a actual transportation model. So we try to incorporate that. Okay. Right, I'll try to, yeah. So I'll continue. I might have to go a little faster for the next portion. All right. So bringing this back again, right? So now we want to take a look at the in terms of the data in specifying that's used to specify models, particularly for integrating behavior or behavioral response or demand response to the transportation designs. Right. So for the use case for this this part is considering, let's say, a resource allocation problem, right? Statewide, you have a single budget and you're determining where to place your budget to develop new mobility services. You might have one or two or more options of different types of service designs to consider. So essentially, it's like a knapsack problem, right? You have a constraint on your budget, and you're allocating the resources to maximize some kind of objective. And for this problem, we're trying to capture the demand response, right? So we're assuming there's an underlying data, right? So the underlying data in this case that we're using is Replica data. So Replica is a company that started out from Google, and they use various data sources to synthesize populations, right? So they have for New York State, all the 20 million residents synthesize agendas from using various data sources, and their data has been validated at around 90% accuracy with respect to census data. And we take that individual synthesized data and aggregate them up to market level, so basically OD pairs at the census block group. Right? So we're using this as our underlying data set to now say, can we develop a model that captures the response in demand based on different allocations of resources? So in the state-of-the-art approaches on modeling choice, right, for example, in capturing ways of differentiating heterogeneous responses to system designs, oftentimes we place restrictions in some way or form, right? So some of the more state-of-the-art methods, and there's many more, right? So like mixed logit, latent class models, some of which were presented earlier in the workshop as well, where you try to fit let's say you have parameters that capture the variations in taste preferences in the user population, right? But oftentimes for convenience in estimation, they might be fit to normal distributions, for example, right? Maybe multivariate normal distributions, but still requiring numerical integration that might not make it very easy to integrate into optimization models, right? Something that we saw from Irene's presentation, why she kind of broke it up into 2 steps, right? And even the logit itself, logit model component, it's hard to incorporate because of the non-convexity. It's been well studied, particularly from Michel Ballard's group, right? Looking at trying to develop choice-based optimization methods. And in particular, this study, well-established study from Stefan Hess's collaboration, right? They looked at the sources of model misspecification from having inappropriate choice of a distribution, a mixing distribution for these kinds of choice models, right? It can be problematic to try to impose some assumption about how they fit. So we went about this, addressing this challenge by, first we looked at a market share model because we're using all the data across New York State, but because of the size of that, we're looking at this at the market level at OD pairs, right? So we use the BLP model for this, right? So market share model where you might have this relationship between the ratio of two different market shares for basically two alternatives for a given OD pair would follow this relationship, right? Where you have market attributes X and coefficients theta, right? And we design a model that allows us to estimate agent coefficients. So essentially, every market, every OD pair, we end up having a different theta. And we do this in a way where we can estimate each of them individually such that it's non-parametric, right? So we also incorporate a set of clusters for these priors so that we don't, it could be bimodal, trimodal distributions, right? So the k-modal distributions. So what this means is if we have 100 by 100 OD pairs and consider 4 mutually exclusive population segments, we're estimating simultaneously 40,000 models with that many sets of coefficients, right? So this is looking at it as kind of like a machine learning, trying to fit the models, the parameters to the data, right? So it's agent-based inverse optimization. And the estimation process itself is a fixed point problem. So basically, we have priors of these parameters that we then try to perturb minimally so that, oops, let me go back to that, right? That we perturb minimally so that the posterior matches up, right? So we have to go through this. That becomes a constraint. The optimization itself is like a least squares optimization, where we make sure the market share ratios are sufficiently close, right? And that we're selecting which cluster also that each of those markets belong to, whether it's like cluster 1 or cluster 2 and so forth, right? Okay, I'm running out of time. So we can decompose this into iterative updates using method of successive averages. There's other iterative methods as well that we've implemented, like a weighted averaging schemes as well that can be faster, right? So as an illustrative example, consider this case with 8 agents, right, or 8 markets that we're considering, 3 clusters that we allow for. And using this technique, we would have something that looks like this, where we've assigned each agent to a cluster, and their parameters are fit in a way so that the variance across them are minimized, and there's consistency in the prior to the posterior of the parameters, and the percentages are fit as close as they can. Okay. So that's how this method operates. And we tested this on, so we run this across the New York State data that we have from Replica. We broke it down to 4 different mutually exclusive segments. So low income, non-low income are the employed segments, and then senior that are not working, right? Seniors that are not working, and students. And we considered 2 possible clusters. So as a result, based on the segments and the OD pairs with sufficient trip data that we have, we end up with about 120 to 121,000 market agents that we're estimating individual parameters for. And in the optimization for estimating these parameters, we restrict them to be non-positive. Right, so this is the results of the estimation, visualization of some of these estimated coefficients that you can see. There's also, we do also compare this visually to using parametric distributions like normally distributed mixed logit model and such. And there's some commonalities and some differences in them. We also did tests with in and out of sample comparisons with some of these benchmark models with mixed logit and conditional mixed logit and the individual parameter logit that Russ recently developed. And so we see that we stand pretty well in the accuracy, okay? So, and when we pull out the specific, some of the numbers of interest, right, like value of time, we see numbers that kind of make sense to us, right? So looking at the statewide level versus New York City level, there's generally a tendency that the value of time in New York City is a little bit higher and the non-low income tends to be the highest average overall, right? So again, these are average numbers pulled from every OD pair that we've estimated the cost coefficients and time coefficients from, right? This data set is also publicly available. So all the estimated mode choice coefficients from the replica data for New York State, as well as the computed market shares, are all publicly available. So the intent is that this can be used as a underlying demand set for doing some optimization techniques or scenario analysis for other purposes. Right, so, and in fact, that's one thing we do, right? So we wanted to see, now we have this set of demand models across the state. Can we use it to support that mobility service knapsack problem that I just mentioned earlier, right, at the statewide level? So we have two service options that we consider, although for this presentation, I only present one of them, service A. Right, so basically, we consider two types of service, one with like a ride-hailing taxi type service, and another that's a more like ride-pooling microtransit service, and look at the demand impacts at different OD pairs, right? So it is, the optimization itself is very simplified to really be more like a bare bones knapsack problem at the statewide level, right? So one thing to try to avoid the non-convexity of the logit models, we note that we can pre-process because there's no dependency here, right? Each market, we assume, we have their own models, and so we can pre-process all the predicted market shares for every OD pair and for every combination of available options, right? Whether there's neither A or B, or one of the two, or both together. And so we can end up actually with a integer linear knapsack problem if we only consider service A, or if we consider both of them, it's a integer quadratic problem program, right? We considered 4 different objectives. We started out with maximizing revenue, consumer surplus, and initially it was minimizing disparity in consumer surplus between disadvantaged and non-disadvantaged communities. But Carol was kind enough during TRB to stop by my student's poster session and educate him about sufficiency. And so we added this as another scenario last night. so it's in there, right? And we consider different budget levels as well. But for this presentation, we only present some of the findings. All right, so as far as disadvantaged community is concerned, we use the definition from NYSERDA, which is the state energy agency, that define different locations that they consider to have disadvantaged populations. Of course, based on all the discussion this week, might not be the most appropriate, but we wanted something consistent to look at, right? And as far as the objective for disparity and the sufficiency, disparity is making sure that high and the advantage and the disadvantaged communities in terms of the consumer surplus after the fact is not too far apart, right? So looking at that whole the Lorenz curve type of impacts, or in terms of sufficiency, what we did was we took that metric from Carol's work. And we changed the metric to one based on consumer surplus because we have that information from our choice models. And we try to minimize insufficiency at the same 10% for our case study, right? So this is the result for the single service scenario at 3 different budget levels. These are 4 different objective results at the second budget level, right? So you can see based on that, the results are pretty consistent when you look at the total revenue and total welfare maximization. And when you look at welfare disparity, you end up with very different results. And the interesting thing is when we look at welfare insufficiency metric, we get something in between. So it's kind of where we're able to still reduce insufficiency overall quite significantly versus not using this metric. And again, of course, we can also combine objectives, right? So here, we're only looking at each objective singularly to make these comparisons. But the neat thing is that we still maintain a lot of the properties of the other objectives in the insufficiency metric. So thanks, Carol, for sharing that with us. right? So, yeah, what we observed was objective 3 tends to focus on shorter trips that start from disadvantaged communities. Objective 4 focus on longer trips that are hard to conduct without a private vehicle. And yeah, it seems to, objective 4, which is the insufficiency, seems to capture social welfare and revenue pretty well while reducing insufficiency. Oh, okay, yeah, I'm about to wrap up. All right, so to conclude, so for this part of the presentation, even with available data for existing behavioral models, integrating them into optimization model problems can be problematic, right? So we introduced this new model that tried to circumvent some of these issues by using a more data-driven approach. And it seems to perform pretty well, and we were able to integrate it with the optimization models as linear or quadratic in binary programs. And the results suggest minimizing inconvenience actually seems to work pretty well, in at least retaining much of the benefits of the other objectives while significantly reducing insufficiency. Okay, so to wrap up, data plays a major overlooked role in equity analysis in transportation. And we showed 2 techniques to try to augment data structures, or how we look at organizing this data, right? One with redistricting the data to try to reduce coverage bias, and also looking at new market share models that can capture these coefficients non-parametrically. And I'll stop there, so.
So why did you do Bayesian estimation in this case? It seemed like a natural application. So you had priors and everything.
Yeah, you can also use the Bayesian optimization, but then Bayesian estimation, but then that also assumes like you have to assume a prior and posterior distribution, right?
We need
so,
distribution.
Yeah.
You could do those non-parametrically as well.
Yeah, that's true. All right, thanks for the suggestion.
Well, okay, so first let's thank Joe for the great talk.